So we're going to talk now about the general framework of network flow. This is an incredibly rich framework. It is a special case of linear programming. Whenever you have a special case of whenever you're specializing the class of problems you can address, you should expect payback in terms of more specialized and faster algorithms, better results, etc. And that is exactly what happens when we're talking about network flow. We're going to see a number of the special and magical aspects of the theory throughout the rest of these lectures. Here we're just going to introduce a few of the main foundational problems of network flow. So the basic object that we care about is a graph. G is a graph, and most often, at least in the beginning, we're going to be talking about, in fact, a directed graph. So that means that it is made up of nodes and a bunch of arcs, so edges that have a direction. So V, let's say we have n nodes, a collection of n nodes, and then E is some subset of V cross V with directionality. So edge 1, 2 being in a graph is different from edge 2, 1 being in a graph. And we're going to see that this is that the basic problems, basic network flow problems, are indeed a special case of linear programming. And because of that, there are specialized algorithms, specialized analysis, special properties, and so on. And we're going to see some of these. So the two problems that we're going to talk about today and in the next several lectures are two problems. The shortest path problem, which I think is natural. Here's my graph. If I have two special nodes, my source and sink nodes, or start and terminate nodes, the shortest path problem, and again, all of these will have certain directionality. In this case, there's actually only one path through the network at all from S to T, but the shortest path problem is one where we want to minimize the cost of choosing certain edges which get us from S to T. So here what we'll want to combinatorialize is the objective function. So there'll be a cost on each edge. We're also going to talk about the max flow problem. So let me write the costs here: 3, C4, C5, etc. The max flow problem on the same kind of graph would, instead of having costs, we put capacities. I guess C is also a good letter for capacity, but because for us we always think about capacity constraints or resource constraints being our right-hand side, AX less than B, it's convenient just to use B. So here, B is not the cost of using a particular edge, but it is how much flow you can pass through an edge, and this defines the max flow problem. So here we're going to want to combinatorialize the right-hand side when we use the primal dual algorithm. Okay, so these are two special cases of network flow, but in the various types of network flow problems, the main concept here, and the reason it's called a network flow, is that we're imagining some incompressible fluid being passed through the nodes of the graph to whatever end. In the shortest path, you want to find the cheapest way to send one unit of flow from S to T when you have uncapacitated incapacitated edges. For max flow, we want to see how much we can push through the graph. The fact that I said it's incompressible is another way to emphasize that we have flow conservation constraints. Other than the supply and demand at a particular node, and just flipping back again, in max flow, we would assume that there is basically an infinite amount of supply at going into S and an infinite amount of demand coming out of T. So except for those, every other node has to satisfy flow conservation. We can't gain or lose fluid. And the basic object that we're going to use throughout is a node arc incidence matrix. So in other words, A is a V by E dimension matrix, and it essentially encodes the graph and the directionality. And basically, the ij element of A is equal to +1. I shouldn't call it ij. I want to call it ij because we're so used to that. But maybe it's more suggestive just for this slide to call this I comma E, because the rows of A correspond to nodes, and I'll use I for that, and the columns correspond to edges. I'll use E for that. So it's +1 if arc E is leaving node I. It's -1 if arc E enters node I, and it's 0 otherwise. So that means that every column of A corresponds to one row. Every column of A corresponds to an edge, and that means that that column will have a +1 and a -1 somewhere, because that edge has to leave one node and enter another node. So just a simple example here, maybe for an even simpler graph than what I just drew. So here's E1, E2, E3. I'm drawing the directionalities. E4, E5. This is T. This is S. Then there are 1, 2, 3, 4 nodes. So that means that my matrix is going to have 4 rows and 5 columns, because there are 5 edges. 1, 2, 3, 4, 5. And you can just go through and fill this out. You'll see this is the first edge. I need to label the nodes as well. So let me label them 1, 2, 3, 4. So the first edge leaves node 1 and enters node 3. 0 everywhere else. The second edge leaves node 1. I guess in my example, my labeling was different. E2 leaves node 1 and enters node 2. The third edge leaves node 3 and enters node 2. The fourth edge leaves node 3 and enters node 4. And the fifth edge leaves node 2 and enters node 4. And zeros everywhere else. So this is an example of the node arc incidence matrix. And flow conservation at node I tells us that what goes in must come out. So let's let F be a vector that tells us how much flow there is on every element of on every edge. Flow conservation at node I is the same as saying that the ith row times F is equal to 0. And if there were demand or supply, then the conservation would be altered by that demand or supply. So what flows in minus what flows out should equal either the additional supply or the demand that I had at that node. So now let's write down the shortest path problem. So this is so we want a flow of unit 1 and minimal cost from S to T. So what is flow conservation? Reads that my matrix A times the flow vector F should be 0 everywhere except for S, because there's +1 supply there. At T, there's -1 supply. In other words, there's a demand of 1, and there should be zeros everywhere else. So in other words, what flows into S minus what flows out of S has to equal 1. And what flows into T minus what flows out of T should be equal to -1. One thing to note is that one of these, not one in particular, this is a redundant set of constraints. So you can check. These are not all independent. These are redundant, so we can omit 1. And for now, I'm just going to be omitting the T. This is the S, T. I'm going to be omitting the T, the row that corresponds to T. But I could have omitted the row that corresponds to S, and everything would essentially work out in a similar way. So the linear program that we want to solve is minimize C transpose F subject to AF is equal to 1 with zeros. So note that row T is omitted. The flow is restricted to be non-negative, but there's something else. Right? So we want to make sure that only a single path is selected because we want the shortest path. And there's nothing in principle that is stopping this linear program from taking fractional values. So we'd like to add the constraint that only one path selected. For now, I'll just leave it to say that in this particular example, it's relatively straightforward to just intuitively argue and convince yourself that this is going to be the case, and in fact we don't need this constraint, and any optimal solution will satisfy it. That's good news because this constraint looks not very friendly for linear programming. But we're going to see in some future lectures that there are very specific and rigorous technical reasons that have to do with the structure of A that guarantee that this is the case. But for now, I'm just going to mention that we don't need this, and also I just invite you to think about, in the context of linear programming, why it would be the case. So imagine that you have a fractional solution. Convince yourself that there is an integral solution that is also optimal. Okay, so this is my linear program that is, I'm going to call my shortest path LP. And onto the second problem that I mentioned, max flow. Instead of costs, we have capacities. But otherwise, capacities. But otherwise, we have flow conservation, and pretty much everything is the same. So what are we trying to maximize? Let me just draw that little network that we had again. Instead of having a unit of 1 and -1 here, supply and demand, instead this is what we want to maximize. We have no cost, so this is going to be, we're going to have a supply of V, which is also a variable of the optimization, and that's what I want to maximize. So I want to maximize V subject to AF. not equal to 0, but equal to v and minus v in place of 1 and minus 1. So I'll just encode that in this way here. Plus d times v is equal to 0, where d is same vector we had before. Minus 1 if I equals s, and plus 1 if I is equal to t. Note that before I had plus 1 and minus 1, but just the way I wrote it, I brought d onto the left-hand side. I don't have af equals dv. And then 0, there's zeros everywhere else. One note here that I'd like for you to check for yourselves is that it's because of A, because of the structure of A, I can also have a less than or equal to sign here, basically because of flow conservation. So just convince yourself that that's true. It'll be useful for us to recognize that because sometimes it's more convenient to use less than or equals. Sometimes it's more convenient to use equality here. Now the new thing compared to shortest path is that the flows are capacitated in addition to having to be non-negative. So this is my capacity vector. In this case, we don't need to make any special arguments about whether a single path or not is selected. You just have a network of pipes. You're trying to push as much water through them as possible. You can split flows. You can do whatever you want. So it's even more clear that this is a linear program. So this is the max flow. This is the max flow LP. Here are our two canonical problems, our two first problems, let's say, that can be written in a network flow setting. And we're going to next attack them using the primal dual algorithm. So it will be nice, first of all, to show what that solution looks like, but also it's going to be a great opportunity for us to get some actual practice with what that algorithm is doing. So we will stop here and pick it up in the next lecture.